Hello folks, and welcome to this introduction to thermochemistry. By the end of this lesson, you should be able to use terminology related to thermochemistry, write thermochemical equations, and draw potential energy diagrams or potential energy profiles. First, let's talk about what enthalpy is. So enthalpy is the energy within a system. It's the heat content of a system. And this is one of the ideas, the idea of the system, that can be sometimes confusing. So, as usual, if you're doing all your studying and your practice and this isn't making sense, make sure you come and see me. The system is your reaction of interest, and everything else that is not your reaction of interest is referred to as the surroundings. So, as an example, let's look at a particular reaction where you were combining sodium carbonate with calcium chloride. So, to react these reactants, what you're going to do is you're going to dissolve them in water first so that your reaction is actually going to happen. So, you're going to take your sodium carbonate, you're going to toss it into a beaker, and then you're also going to be tossing in your calcium chloride as a solution as well. When you mix these things together, you are going to get a precipitate of calcium carbonate, and then you'll have sodium ions and chlorine ions left over. Now, these ionic compounds and the calcium carbonate you get as a result of it and the ions that are left over, those are the system. The surroundings are the water that everything is happening in, and the beaker that you have, and the air that is outside it, and so on and so forth. So yeah, the system is the actual reaction itself. The surroundings is everything else where it's happening. The water in this case is not part of the reaction, it is just where the reaction is happening, and so that is part of your surroundings. Now, hopefully, at some point in your life, you have noticed that with reactions, sometimes the reactions release energy, and sometimes they gain energy. So when it releases energy, you feel that things are hotter. And when it absorbs energy, things get colder. Or sometimes you see that energy released as light. But at any rate, hopefully you've noticed that energy changes have happened. This energy change is referred to as an enthalpy change. The way the enthalpy change works is that you take the total heat of all of your products and you take and subtract the total heat of all of your reactants, and that change, that difference, is what you notice when it comes to those changes in energy. Now, something for you to note, that the heat of your reactants in general and the heat of your products in general, the enthalpy of these items, are not really something that you can measure or calculate, but I'll go into that a little bit more near the end of this lesson. Right, to go into a little bit more of that terminology, you might have heard these terms before. You have exothermic and you have endothermic. Exothermic is when energy is released into the environment or into the surroundings. Now, that means that your reactants have more energy than the products. So, because your reactants have more energy, they release the energy while they're becoming the products. On the other side, you have endothermic. Energy is being absorbed in those cases, and this means that your reactants have less energy than your products. So, because your reactants have less energy, to become the products, they needed to absorb energy from the surroundings. Now, how can you express these thermochemical information? Well, you can write them as equations, for one. When you're writing your thermochemical equations, it's like you are writing a balanced chemical equation, but you are adding in that enthalpy information into your equation in one way or another. So you're going to be including information about that is being absorbed or released. You can put that thermochemical information inside the equation or outside of it, and I'll show you how that works in a bit. And it is also going to be stoichiometric. So all of that stoichiometry, all of that balancing that you do, this is all going to be related to that. So as an example, let's take this situation. You have 0.85 grams of carbon, you combust it. When you do that, it releases that much heat. So first off, let's write a balanced chemical equation for this, as so. And then we're going to add in the information on heat. Now, because of the fact that it is releasing heat, that means your reactants had more energy than your products. So because this has more energy than this, that's why energy is being released. So that means energy is added to this side. So if that didn't make a lot of sense, let's look at it this way. Let's say that your reactants had this much energy and your products had that much energy. In a thermochemical equation, you are going to be balancing all of the elements themselves, but you also have to balance the energy. So the energy on both sides have to be equal to each other. Now, to have these lines, these amounts of energy to have an equal value to each other, you either have to subtract energy on the left side, or you're going to have to add energy to the right side to make the energy levels equal. Now, when we're writing chemical equations, we're not subtracting things from them ever. We're always going to add them. And so, basically what you're saying is, here are where my energy levels are at in terms of my reactants and my products. To make these energies equal, I have to add in this much to get to where my energy of my reactants were. And so that's the amount of energy that you're going to be adding on to the appropriate side, which in this case is your products. Now, what number do we put in here? We're going to put in the energy, amount of energy, but remember that it's stoichiometric. So we have to write it for, if you have 1 mole's worth of carbon, how much energy will be released. And if you do that calculation, you're going to get 343 kilojoules. Because this is how much it is for your 0.85 grams, so change it to moles. So for 1 mole, that's how much energy would be released. As I mentioned, this energy bit in a thermochemical equation can also be written outside of the balanced chemical equation. And when you do that, it's going to look something like this. So here's a balanced chemical equation, and then to the side you have your enthalpy value, your delta H, for this reaction. And in this particular case, whenever you have an exothermic reaction, you're going to have a negative enthalpy value. The reason for this is the energy of your products is smaller than your reactants. So small number subtracted by a big number. When you're finding the difference of something, it's always final minus initial. So smaller number subtracted by bigger number, it's going to give you a negative number. That means if you're ever seeing positive delta H values, those are endothermic reactions. Now, in a lot of what you're going to end up do later on in this unit, you're going to usually see that delta H has a little knot in there. That knot is referring to standard conditions, which is 25 degrees Celsius and 100 kilopascals, and I'll probably remind you of that later on. To finish off this lesson, let's talk graphs. So we're in the sciences, we love our graphs, and you can take a thermochemical equation and express it as a graph as well. So we do have 2 types, one being enthalpy level diagrams and the other being energy profiles, and the 2 generally show the same information. Energy profiles just has a little bit of extra information. So first off, if we take a look at what the graph looks like, you have in your x-axis the progression of the reaction. The progression of reaction is it's sort of a more generic time lapse without actually going into what time it is in terms of the reaction that you're looking at. And along our y-axis, we have our potential energy. Now, something that you're going to notice is that even though we have these graphs, there are not going to be any numbers on any of these axes. So if we take the reaction from the last slide and make it into an enthalpy level diagram, this is what it's going to look like. So in the beginning of your reaction, you have your reactants, and you have your products as the reaction goes by. And we know that this is an exothermic reaction, and so your reactants have more energy than your products do. And so your reactants are higher up than your products. So there are no actual numbers on these axes because remember, we don't know how much potential energy individual elements and compounds are going to have. What we can find out is the change in energy when a reaction happens. So the only numbers that you're going to see here are going to be related to that change in energy of the reaction itself. So if you are drawing an enthalpy level diagram yourself, doesn't matter exactly where you start, no, not really, but before you start drawing, consider if this is an endothermic or exothermic reaction, and then make sure you're giving yourself enough space within the area of the graph itself to be able to draw everything that you need. This is going to become a little bit more complicated when you do have a multi-step reaction, and so making sure you have enough space and making sure those spaces are relatively proportional to each other is going to be important at that point. Now, if we're looking at an energy profile, you're going to see that it looks very similar. You have your reactants on your left, and on the right side, you're going to have your products. You are going to include the energy difference, that enthalpy of reaction in there as well, but you can see that there's a little bit of a bump here. And this bump is activation energy. I'm not going to talk too much about activation energy here because that is a topic that's more relevant to other learning outcomes, but every single reaction, whether it is exothermic or endothermic, has activation energy. And depending on how much it is, it's going to be bigger or smaller, but you're always going to see a bump that will go above whatever the highest energy between your reactants or products are going to be. So, enthalpy level diagrams, no activation energy. Energy profiles, yes, activation energy. Now lastly, I just wanted to show you what an enthalpy level diagram would look like for an endothermic reaction. Here it is. As you can see, it's pretty similar. Endothermic means your system is absorbing energy, so you can see that the energy of your products is higher than the energy of your reactants. So again, this is exothermic and this is endothermic. That's it for this lesson. I'll see you next time.